So in electrochemistry, we had 3 types of electrodes. The first one, I mean, this is one type where you just had ions. So what you would do in that case was, you're going to take a beaker and you're going to put both ions in that beaker. It's going to be SN4 plus as well as SN2 plus ions. They would both be added. So they would both be added into the beaker. As just to remind you that this is paper number October, November 1943. So they would both be part of the solution. And once they're part of the solution, if SN4 plus likes to gain electrons or SN2 plus likes to lose electrons, we need to give it a source of electrons. So you add a platinum catalyst that is added. And that platinum catalyst acts as the electrode. So for example, SN4 plus starts to gain electrons and starts forming SN2 plus. Then the platinum catalyst would become electron deficient. It would become positively charged because all the electrons are being gained by SN4 plus. Vice versa, if SN2 plus, the reverse reaction is favored. SN2 plus likes to lose electrons to form SN4 plus. Then there would be a lot of lost electrons on platinum and the electrode would become negatively charged. So the point was that higher or more positive E naught means that the substance likes to gain electrons, and lower E naught meant that the substance likes to lose electrons. Those were your 2 main points in electrochemistry. So the electrode would be made out of platinum in the first case. In the second case, if you have a metal and a metal ion electrode, then the metal ion itself, the metal itself can act as the electrode. Okay, for example, you have aluminium and you got Al3 plus ions. So the thing is, the metal itself can act as the electrode. So if aluminium really likes to, and again, the same thing would happen, a reaction would start, either aluminium ions would start gaining electrons to form Al, or vice versa. If aluminium starts to lose electrons, there would be a lot of electrons accumulated on this and the electrode would become negatively charged. But anyways, the electrode in this case would be made out of aluminium. So when there is a metal around, you make the electrode with the metal itself. Okay, is this clear? Yes or no? I said, then you've got, you think that there's a standard concentrations and the 2 electrodes, I think, are connected together. So he's saying, use the Nernst equation. There was a Nernst equation, which is the standard electrode potentials are given in the data booklet, which are E naught. Z was the number of electrons, log of oxidized species, its concentration, divided by the log of the reduced species and its concentration. So first thing, we're talking about the tin reaction. So in the tin reaction, it's tin 4 plus 2 electrons in equilibrium with tin 2 plus. So we need to find what the E naught is. So I'm going to open the data booklet and I'm going to look for the E naught of this reaction. So it's somewhere over here in S. Tin 4 plus with tin 2 plus, and that's 0.15. So we have E naught, which is 0.15. 0.059 is a constant. So we've got 0.059 divided by Z, which is the number of electrons, which in this case is 2. And log of oxidized species. Oxidized species is the one that's formed after oxidation, after losing electrons. Well, that's tin 4 plus. So the tin 4 plus concentration is given as 0.3. Divide by the log of reduced species. Reduced species is the one that's formed after reduction. So that one is given as 0.15. So can anyone tell me what the value is for this one? What are we getting? Please try and calculate this quickly. You can remember this is the Nernst equation, which finds electrode values for non-standard solutions. Lubena, have you done this? Ethan?
0.16.
0.16?
Yeah.
So you're getting 0.16. So originally the value was 0.15, now it's 0.16. Why? Because the concentration of tin 2 plus is decreasing more. So that means the reaction is actually moving in the forward direction. The equilibrium would shift to the forward direction. Tin 2 plus decreases more compared to tin 4 plus. Tin 2 plus has a lot lesser concentration, so the equilibrium shifts to the right. And whenever the equilibrium shifts to the right, the potential would increase. It's going to become more positive. If it shifts to the left, it's going to produce more electrons and the electrode would become negatively charged. So also remember that. Now calculate the E cell under these conditions. So you've got your two electrodes. The new electrode over here has a potential of 0.16 volts. So this one is 0.16 volts under the non-standard conditions. What are the potentials for aluminium electrode? They're probably in A. So it's minus 1.66. So this one is minus 1 point. So what's the potential difference? Higher potential minus lower potential. So it's going to be 0.16 minus 1.66. So we are going to get what?
1.82.
Yeah, that's the value that we're getting. Now, aluminium ions produced by electrolysis of a melt containing large amounts of aluminium ions. So it's this happening. Aluminium ions turning, gaining 3 electrons to form.
Sir?
Yes.
Sir, you have skipped one part.
So for the overall cell reaction that occurs, this one. The overall cell reaction is you had two reactions. You had tin 4 plus in equilibrium with tin 2 plus, and this was 0.16 volts. The other one was Al3 plus 3 electrons, and it was Al, and that was minus 1.66 volts. Now the rule is that the lower potential is the one that likes to lose electrons. So this is the one that's going to lose electrons. It's going to get oxidized. The higher potential is the one that likes to gain electrons, and it's going to get reduced. Or so the higher potential is the one that's going to get oxidized, sorry, reduced. It's going to gain electrons. So you add them up. You add the reactants, you add the products, but before that you have to make the number of electrons gained and lost equal. So how do you do that? You multiply this by 2. So this would become 6. This would become 2 as well. You multiply the first one by 3, this would become 6, and this would become 3. Now if you add them up, it's going to be 3 SN 4 plus 2 Al 3 plus, and the products are going to be 3 SN 2 plus. And I've actually written this incorrectly. Just a second. It's not going to be this. You're going to add up the reactants. In the first one, the reactant is 3SN4 plus. And in the second one, the reactant is 2Al. And the products are going to be, in the first one, the product is 3SN2 plus. And in the second one, the product is this one. It's 2Al 3 plus. So that's going to be your reaction in this case. Okay, is this clear? Okay, I've added up the reactants and I've added up the products that are formed. And I had to make the number of electrons gained and lost equal. So now he's trying to make aluminium and he's asking you to calculate the mass of aluminium that's formed. So the current and the time is given. So it's Q is equal to IT. You can find out the charge. If you do that, can somebody calculate? It's a large current of 300,000 amperes multiplied by 24 hours, which is 24 into what is 1 hour 3600 seconds. So what do we get for this? What's the charge that we're getting?
2.592 times 10 power 10.
Power 10 coulombs. So that's what you're getting. Now, using that, you can find the moles of electrons that are passing through the circuit, because 1 mole of electron has the charge that's equal to the Faraday constant, which is 96. 500 coulombs. You have to remember that as well. So if you've got 2.59 times 10 power 10 coulombs, so how many moles of electrons are actually passing through the circuit? So this, if you solve this, the moles of electrons, they come out to be equal to what? It's going to be 2.59 into 10 raised to the power 10 divided by 96, 500. What do you get? How many moles of electrons do you get?
Two point six times 10 power 2.69 times 10 power 5.
What 2 point?
2.69 times 10 power 5.
69 times 10 power 5. Moles of electrons, right? So 2.69 into 10 power, and you're getting 5. So that's the moles of electrons that you got over here. Now you can find the moles of aluminium by dividing that by 3, because it's 3:1. So you're gonna divide that by 3. You'll find the moles of aluminium. What do you get for that? Like we found the moles of aluminium.
9.95 times 10 power 4.
So this one is coming out to be 8.95 times 10 power 4 moles. I mean, this moles of electrons were 2.69 times 10 power 5. So you just had to divide that by 3, and you found the moles of aluminium. And they were interested in the mass. So you can find mass by, the aluminium is 27. So multiply it by 27. So it's moles into AR. So what's the final answer?
2.42 times 10 power 6.
And that's going to be grams. So you're getting grams for this. And then you've got to explain why chromium metal cannot be obtained by the electrolysis of dilute aqueous chromium 2 sulfate. Your answer should include data from the data booklet. You're seeing why electrolysis cannot give you chromium. I'm just going to repeat the first question. Q is equal to IT got you the charge. Remember, the Faraday constant will get you the moles of electrons. Like 1 mole of electron has this much charge. So the charge that you have, that translates into these many moles of electrons. Once you have the moles of electrons, you can find the moles of aluminium, and then multiplied by AR, you'll find the mass. Now, here's the electrolysis that's happening. Now, in electrolysis, you've got 2 electrodes. One is cathode, one is anode. This tinier one is the negative. So that one is your negative cathode. That's the place where electrons are gained. Reduction happens. Remember, electrons are going to be gained only because the battery is constantly giving. Anyone who comes over here gains electrons. Now it's chromium 2 sulfate. So there's going to be chromium 2 plus ions. The sulfate ions would be at the other end, where they would be losing electrons. We don't care about them. So he's saying, why does chromium metal Why can't it be obtained? That's the question. I mean, apart from in aqueous copper 2 sulfate, what other things would be present in the solution?
H2O.
Which thing?
H2O.
Okay, it's going to be H2O there. Okay, remember, there's not going to be any H+1 or OH ions. So our task is who's going to gain electrons, whether it's going to be chromium 2 plus or H2O. One of the two, battery is sending electrons. So one of the two is going to gain electrons. And who likes to gain electrons? The one that has a higher E naught. The ones that have higher E naughts, they're the ones that like to gain electrons. They're the ones that become positive because they're constantly gaining electrons. So the electrode becomes electron deficient and becomes positive. So chromium 2 plus, where's chromium 2 plus? This one. There's only one. So you got chromium 2 plus, and the value for that is minus 0.91 volts. So I'm going to circle that value. It's minus point. Chromium 2 plus gaining electrons. So that's the only one where chromium 2 plus is gaining 2 electrons. That's it. Who else? Water gaining electrons. So there's water gaining electrons as well. Minus 0.83. So who's more positive? It's definitely water. That's the higher potential. That's the one that's going to gain electrons. So this is exactly what you're going to write over here. That water is the one that's going to that really likes to gain electrons, and it's more positive. It has a higher potential, likes to gain electrons. Is this clear? Do you get clear? Or yes or no? Is this clear?
Yes.
So remember, the higher potential is the one that likes to gain electrons. Then you're being asked to draw the Dorian-Krauss diagram for the ClNO2 molecule. So each molecule nitrogen atom is bonded to chlorine atoms and bonded to each of the oxygen atoms separately. So there's a nitrogen atom bonded to a chlorine atom. Now chlorine would only form a single bond, and it's bonded to 2 oxygen atoms. Now oxygen likes to form double bonds, right? So Cl has 6 electrons left. O has 4 electrons left. N will have a lone pair because it's sharing 3 of its electrons. So out of 5, there are 2 left. So what would the last oxygen do? The last oxygen would probably form a additive bond because oxygen has a total of 6 electrons. So it's going to get 2 electrons from nitrogen. That's it. And its 8 electrons will be completed. So the last one would be a additive bond. I mean, this one over here is a additive bond. Because nitrogen's outer shell was already complete after bonding to Cl and oxygen. One bond over here, it got 2 electrons, 4 electrons over here. That's 2 over there. So that's a total of 8 electrons. So nitrogen's bonding was already complete. The only thing that it could do was it could form a additive bond. Like it's not going to gain electrons from the other atom, but it can give electrons to the other atom. So it needed this oxygen atom needed 2 electrons, and nitrogen ended up giving those 2 electrons. And then he's saying, right, the rate equation we just did. He didn't tell us what the orders were. He actually did. It's first order with respect to each. So it's going to be K. ClNO2, that's going to be order 1. And NO is going to be order 1 as well. So it's going to be order 1 with respect to both of them. Reduce the units of the rate constant K. So concentration per second. So this is X S minus 1. K into X mole per dm cube into X mole per dm cube. So if I get these two X on the other side, this would become X minus 1, S minus 1. So it's going to be mole minus 1, dm3, and S minus 1. Is this clear?
Yes.
And then he's saying, state and explain whether or not the reaction would take place in a single step. Yes, it can. Because it's order 1 with respect to both. So if it's a single step reaction, like let's say this is the reaction, there are no more steps. So this is the step on which the rate depends. I mean, this would be your rate determining step because there is only one step. You speed this step up, the reaction speeds up. You slow down this step, the reaction slows down. So if there's only one reaction and there's only one step, then that step is the rate determining step. So that means the rate of the reaction would be dependent on both of them because that's the only step you have to speed up. Is this clear? And then you have to experiments carried out using initial concentration 10 power minus 4. A large excess of NO is used. The reason you use a large excess of NO is so that one of the reactant becomes constant. So that means your rate is now only dependent on the concentration of ClNO2. NO is going to be completely absent from the effect because it's in large excess and its concentration would be kind of constant. So you think draw a graph to show how the concentration varies for the first 0.2 seconds. I think we did this type of question in class. We can skip this one. We can go to entropy, or I can just go through this one very, very quickly because he's already given us the initial starting concentration of ClNO2. So that's 2 times. So you're going to start over here. I mean, that's the point. And he's given us the rate of the reaction. The rate of the reaction is M. It's the gradient. This one is the gradient. And it's going to be a negative gradient. So it's going to be y is equal to minus mx plus c. We have the c value as well. That's the starting concentration. We have the c. We have the gradient, which would be a negative gradient because the concentration would go down. So all you have to do is use this value. And he's saying at the 0.2 second mark. So x is time. So I'm going to put in time over here. It's going to be y is equal to 1 times. So it's going to be 1 times 10 power minus 4. X, which is, so we can look at 0.2 seconds. Plus c is 2 times 10 power minus 4. Can anyone tell me what the value of y comes out to be? What do you get for this? And remember, I'm going to just repeat this. ClNO2 is the reactant. Its concentration at the beginning is this thing, 2 times 10 power minus 4. And the rate of the reaction is given. The rate of the reaction is I mean, whenever a reaction happens, its concentration starts to decrease. The reactant concentration starts to decrease with respect to time. So they gave us the gradient, the rate of the slope, and they said specifically that the rate is assumed to be constant for the first 0.2 seconds. So it was coming out to be a straight line. The reaction was happening at a very at a constant speed. What do you get for y? Anyone, what are we getting for this?
I get 1.8 times 10 power minus 4.
So we're getting 1.8. So something over here at 0.2 seconds. So that means it's going to be, I mean, you're going to get a line something like this, Tika. That's what you're going to get. And we can skip that. We can go to entropy. The rest is just graph questions. Deduce the concentration of NO2 product at 0.2 seconds. We just did that. No, he's talking about the product. So if ClNO2 concentration decreases to 1.8 times 10 power minus 4, so that means there's a decrease of 0.2 times 10 power minus 4 mole per dm cube. So all of the reactant must have changed into product. So if ClNO2 decreases, NO2 is formed. It's 1:1. So the amount of NO2 formed would be exactly the same. So if the reactant gets used up, I mean, this is the amount that's getting used up, 0.2 times 10 power minus 4. All of that turned into the product. So the product would be 0.2 times 10 power minus 4. Is this also clear?
Sir,
Yes.
for solving the point at 0.2 seconds,
Yeah.
you just use the gradient to find the answer.
Why did we?
Could you just use the gradient instead of the equation to find the answer?
You can do that, but how do you plot the gradient? Like y2 minus y1 and x2 minus x1?
Because the gradient is changing y and changing x.
I mean that's
So
that's
the
pretty.
x is 0.2.
That's pretty much going to
And
give you
because
this.
the gradient is
That's going to give you the same expression.
1 times 10 power minus 4.
That's a gradient, right? And it's going to be minus 1 times 10 power minus 4, right? And you have y1 and x1, like that's the first point. And you have x2 as well, because he told us the time as well. The only thing missing was the y-axis. So you're going to find that. So you're going to get the same expression over here. Is this clear? And so after 20 seconds, the concentration of ClNO2 remains constant. That means the reaction has stopped. Like it's not changing. That means it's an equilibrium reaction. So I think equilibrium is reached. Like if you look over here, this had double arrows. So the backward reaction must have started. So the amount of ClNO2 stops changing. That it reaches equilibrium, and no matter if it gets used up, the same amount gets produced back again. So the rate of forward reaction and the rate of backward reaction, it kind of becomes equal. Okay, is this clear as well? That the concentration was initially decreasing, but then it becomes constant. That means equilibrium is reached. Clear? Yes or no? Is this clear?
Yes.
Achha, what is
Sorry.
yes?
How could you tell it was a negative gradient again?
So I could tell if it's a negative gradient because reactants always have a negative gradient. Like reactants would always go down. Like you start off, the reaction starts, and the concentration starts to decrease.
Yep. Thank you.
If it had been the product, then the product would have a positive gradient. It's going to go up. The value of the gradient would be kind of the same, but plus and minus, it would be pointing upwards or downwards. That's the issue. So what is meant by the term entropy of a system?
Measure of disorderness.
It's a measure of disorder of a system, and you've got what's the entropy change over here that's happening and why? What's the entropy change? Liquid water cooling down. So disorder is decreasing. And why is it decreasing? Because molecules are losing kinetic energy. So there's going to be less disorder. Okay. Is this going to be a large change or a small change in disorder?
Small change.
Okay, it's going to be a very small change. Okay, because by just looking at it, water at 80 degrees centigrade kind of looks exactly like water at 60 degrees centigrade. So it's going to be a very small entropy change, but there's going to be an entropy change, but a very tiny one. It's going to be negative because they're losing kinetic energy. So there's going to be slightly less disorder. As a calcium chloride is added to water and the mixture is stirred, what's going to happen? And disorder increases or? It's going to be positive. There's going to be a large increase in disorder because previously the ions were held together in a lattice. They were very orderly. And then when you mix them in water, what would happen? The ions dissociate in aqueous state. So they become very disorderly. Is that clear? So all the ions,
Yes.
they get scattered and they dissociate. What about the last one? You've got the enthalpy change corresponding to the lattice energy of calcium chloride. So it's calcium, lattice energy is calcium gaseous ions, Cl gaseous ions, turning into CaCl2 solid. But what's happening? Disorder decreasing or increasing?
Okay.
So
That's
this,
solid.
okay, that's going to be negative, not exothermic. I mean, this is not exothermic, it's just a decrease in disorder. And I mean, the reaction is exothermic. Why? Because you're forming a regular lattice now, and a solid is being formed. So gas molecules decrease, because remember, gas molecules have the greatest amount of disorder. And they turn into solid, which is a regular lattice. So they become more orderly. Disorder decreases. What's the full name of delta G?
Gives free energy.
Plus you have to write standard as well. There's a knot on top, so that standard gives free energy. Describe how the temperature at which the reaction becomes spontaneous can be calculated. Include an equation in your answer. So what's the, how do you calculate spontaneity of a reaction?
Delta S.
The equation that you have is
T
delta G
minus delta S.
delta H minus
delta
T
S.
minus T delta S. Okay, that's the Gibbs free energy, right? So for a spontaneous reaction, what should the value of delta G be equal to? For a spontaneous reaction, delta G has to be exothermic. It has to be less than, it's got to be less than 0, less than or equal to 0. Because delta G is the overall energy change of the reaction. It includes the enthalpy change, the heat energy that is produced or consumed, plus it's the disorder, the energy or work done produced because of the disorder. So delta G has to be less than or equal to 0. It has to be exothermic. So that means delta H minus T delta S must be less than or equal to 0. And you can then, what you can do is you can make T the subject of the equation. So T would become greater than or equal to delta H divided by delta S. Is this clear? And you can solve for T. So is this clear? Yes or no? Is this clear?
Yep.
So let's continue tomorrow. We'll do organic on Monday. We'll probably have a past paper class tomorrow. Okay? I'll let you know the time of the class as well. So, okay, everyone. Take care. Allah Hafiz.
Thank you.